All right, well, my name's S03 Kauffman, and I teach at Albright College, and I work with the Pottstown, Norristown, and the Lancaster groups. And I started life as a geologist, and then I became an environmental scientist, and I wear lots of different hats. Environmental science is my love. Geology is what was my first love, and it's what I'm mostly teaching right now. So I was a little punchy at the end of last week when I was putting this together. And so I decided to give our investigation an overarching theme of sort of climate detective work. And so my family's obsession with Sherlock Holmes and all things Sherlock Holmes is going to pop up throughout the presentation, so I apologize for my corny sense of humor. So often when we are teaching environmental science and we're teaching climate change, we sort of give students, we give folks what we know. We say, here's the list of greenhouse gases. This is what they do. But I wanted to kind of have us dig a little bit into this to understand the reason why the greenhouse gases do what they do, why they are listed as being, some of them having greater warming potential than others. And I really wanted us to get to the kind of physical chemistry side of the story. So that's what our activity is going to lead us to do today. We're going to be working with the electromagnetic spectrum, which you guys being high school teachers, I don't have to spend a lot of time on this with you, but just to warm us up, get it? Just to warm us up to what we're going to be looking at today. Where does the sun's, where does the sun emit radiation in the EM spectrum? Ultraviolet, somebody said, okay, we have a sense that ultraviolet light comes from the sun, so that's a great intuition, observation, or piece of knowledge. What else? What? Infrared, we know that the sun also throws off heat, and heat is the part of the infrared spectrum. Well, that's where we get heat from, is the infrared part of the spectrum. Anywhere else? Visible, right? Okay. We've sort of evolved these eyeballs to be able to see the spectrum of light that's put out by the sun. That's called our visible spectrum of light. Can we see? Do we have X-ray vision? Not unless we're a superhero, right? We don't have X-ray vision, not us regular human beings. That's a different part of the EM spectrum. He does? You have X-ray vision? Sweet. Yeah. Did you ever have a sense when you were a kid you had like a superpower that nobody else had? Like you wanted to imagine that you really could see like through things, or I don't know, maybe I was just a weird kid. But so here's the sun. I kind of flipped the spectrum here. So the sun's part of the spectrum peaks here, right around the edge of the visible light into, well, over into the ultraviolet here. And then the Earth's spectrum, okay, so the Earth isn't glowing. The Earth isn't giving off light in the sense that the sun, in the way that the sun is giving off light. What is the Earth giving off? It's giving off infrared radiation, right? So in order to see the infrared radiation on Earth, we've heard a lot about this at NASA, lots and lots and lots about infrared spectrum, right? Yes, we're gonna just kill this infrared spectrum for one more week.
So just a little bit of the UV is where the sun's emitting.
Yeah, actually, yeah, but it's
a lot.
But it's really high energy, right? So the tighter the wavelength is here, the higher the energy that's emitted there. So even though it's in the UV spectrum, it's high energy radiation. So it has a lot of bang for its buck, so to speak. All right, again, this activity may be a little beneath us, but we'll do it anyway. Historically, we created light bulbs that were incandescents, right? And then we eventually said they're too inefficient. We created fluorescent light bulbs like the ones in here. And now we're saying, oh, we even have something better. We have LED light bulbs. So I'm going to show you the spectra for the sun in yellow, and then 3 light bulbs, the red, the blue, and the green. First question's the easy one. Which one of these curves represents the incandescent light bulb?
The red one.
Why the red one?
Because they produce a lot of heat.
Yeah, see where this peaks? And where most of our energy is being expended is in creating heat. And anybody that's put their hand on an incandescent light bulb knows this fact very well. It's really hot. It is inefficient because we're not trying to create heat from a light bulb unless we have an easy bake oven. We are trying to create light. And so we'd much rather have a light bulb that peaks here in our visible spectrum, right? So we have 2 light bulbs that can do that. Fluorescent, we can do it better. Fluorescent and LED. Which is fluorescent, which is LED? Green and blue. Why? Why would LEDs have peaks? Just trying to see what those peaks represent. What are those?
Emitting diode, and so that means.
Anybody else have a thought? Who's a chemist? Okay, chemists, help us.
Well, I know that fluorescents emit high like mercury wavelengths, so maybe the green. It has 2 strong lines.
Mercury has 2 strong bands?
Yeah.
Okay. So chemists can usually pick this out because they know the spectra for gases. Do you do this with your students where they look at, and if you're in a room that has fluorescent light pollution in it, you will pick up spikes sometimes of mercury from those fluorescent lights. Have you had that happen?
Yeah.
Or when you don't look at spectra with you?
I don't have,
okay.
I don't have the equipment. We would have pictures and stuff.
Okay, okay. Well, if you actually did the the visualization, you would get, you have to be in a really dark room in order to not get light pollution. So you would get mercury spikes, which is actually a good teaching tool in itself. So these are mercury spikes coming off of the mercury in our LED lights. Kind of cool. We're seeing the emission spectra for mercury show up in these lights. LEDs have what we consider a more natural, more sunlight-like spectrum of light. They're supposed to be better, healthier for us because our eyes are used to looking at a spectrum of light historically or evolutionarily that mimics what's coming from the sun. So the best light bulb for us would be something that's pretty close to that. So there's also some, purported health benefits to moving from fluorescents to LEDs. Whether that plays out or not, I don't know. But there have been studies about the influence of fluorescent lights on people who live in office buildings and schools and places where the only light source is fluorescence. Hopefully you all have windows, right? No windows? Oh, that would kill me. They took your window. How can they take windows away?
Built a new section of the school right over my window.
I thought they were legislated that they had to provide natural light in schools. No?
He doesn't have that.
No, we don't have any. They replaced our windows with like not so transparent plastic stuff. So you can't even tell what time of day it is. When you walk out of the building at night, you're like, oh.
I'm so sorry. That sounds awful. I said when they put me in a classroom that doesn't have windows, I'm like, I'll go teach in my lab because I can't be in.
One day I do this lab.
The one.
Because it's completely dark.
Right. That's it. Well, that one day out of 180. Woohoo. All right. So this is a kind of fun little thought experiment that has a very real world application. And there is our answer. All right. I'm not gonna go into the depth that you would do with a chemistry lesson, but what we need to understand for today is this. When infrared or any radiation hits an atom or a molecule, it has a certain amount of energy that allows it to do different things. High energy radiation allows ionization. Ultraviolet radiation allows electron level changes. Infrared radiation allows something called molecular vibration. And for this, I need you all to stand up and assume the position of a methane molecule. Methane is CH4. So loosely, you can make your torso the carbon. You can make your hands and your feet the hydrogens. And And I just love these terms. I'm not a chemist, but I love what these molecules are able to do. They are able to scissor and rock and wag and twist. Chemists have the most fun. Here, let's look at this. So we are going to be vibrational molecules. So you can imagine right now a blast of infrared radiation coming at you, and pick your favorite vibrational mode. Each mode here, I'm serious, do this, don't. So each mode will show a little bit different absorption peak in the absorption spectrum. So we can twist, I don't know what that twist is really doing. Twist? I'm not really sure. Scissoring, that one seems kind of easy. Rocking, we can twist, we can, oh, I'm sorry, those are stretches, now I see it. We can scissor, that's this way, and we can rock. Wait, nobody's bending at the hips, we have to, there you go. So this is what you are doing if you're a methane molecule, or you're any kind of molecule that is able to vibrate by bending or twisting when infrared radiation hits you. So, have a seat. Let's look at one of our favorite gases. This is a diagrammatic version of carbon dioxide. So when carbon dioxide, because it has a slightly negative side and a slightly positive side, when it is hit by a wave, it will kind of bend as that wave comes in here. These are flat versions of what we were just doing. So here's a question for the chemists. Oxygen and nitrogen, diatomic gases, do they have vibrational movement? Vibrational modes. You don't get into vibrational modes, do you? Not at all. Right, right. No. They need to be able to, they need sort of an imbalance in their charge, basically a dipole or an asymmetric, like a carbon monoxide, there's an asymmetry there, so it can stretch in one direction a little bit. But when you have something like oxygen, which is two oxygens, boom, bound together, there's no ability for that to stretch. There's definitely no bending or any of that other stuff either. And so oxygen and nitrogen, what's going to happen when infrared radiation hits them? Not a whole lot, right? So they don't absorb it. So they're not greenhouse gases. I'm telling you this, but I want you to discover this on your own. And so what we're going to be doing is an activity that lets us do that. All right, so we are 15 people, so I'm going to take 3 groups of 5. So let's do 1, 2, 3, and then you guys, if you want to come around and join them here, you'll be one group of 5, and then if you want to flip around and join these guys, and then, or do we have more than 5? We have more than 15. You have to leave. Okay.
I can be with it.
All right, why don't you come over here then? All right, and then we'll do the 5 in the back. But it'd probably be easier if 2 of you came around this side so you could kind of chat and work together. And then you group of 4, okay? So let me think about this. What I'm going to do is I'm going to give each group a piece of the spectrum. So one of you is going to have this part of the spectrum, the sun. And what you're going to be looking at is the ability of a gas to absorb radiation in this part of the spectrum. The other 2 groups are each going to get half of this. So one of you are going to have this part, the other of you are going to have this part. You are going to be looking at the ability of Earth's atmospheric gases to absorb radiation. Okay, so if the surface of the table is the Earth, here's our atmosphere. The first group is looking at the ability of the atmosphere to absorb the incoming radiation from the sun. The other group is looking at the ability of the atmosphere to absorb radiation coming off of the Earth. And that we know is in the infrared spectrum, part of the spectrum. Okay, is that clear? Somewhat clear? Okay, so groups 2 and 3 will have this, sliced down the middle, and group 1 will have this. So, activity 1. Who has 4? All right, I'll give you guys the sun. So, and I invite you, I have rulers. Actually, before we get started, I need to point out one more thing. But I have all kinds of supplies if you want them. That's the wrong one. All right, who's my group 2? We're about 5, right?
Incoming out.
Oops, I need group 3. All right, let's see if we have. Yeah, I think that's good. All right, so let's get a working kind of arrangement here. So if I could just have your attention just to get you started with this. Because this isn't probably something you've done in a long time or never, maybe. All right, so the top curve here is the front side of the Earth's emission spectrum. So the Earth is emitting infrared radiation according to this curve here. What these blue plots represent is the absorption of atmospheric gases. So in the case of CO2, what I'm going to do is I'm going to try and get you started with a representative over here. So if this is our emission by the Earth, and that little blip of CO2 represents absorption, if I wanted to draw this on the curve, how am I going to represent the absorption of that radiation by the carbon dioxide gas?
It would drop out of the curve.
You would draw what?
It would drop out.
It would drop out, right. So if I drew it this way, I'd be saying that my emissions actually increased, which doesn't make any practical sense. So we actually have to look at these curves, kind of flip them upside down. And so what I'm going to do is say, all right, from, let's say 4 to 4.5, if this is 4 and this is 5, 4.5's right there, I need to make a peak that looks kind of like the one on this graph. Now, next question is going to be, well, how big do I make it? Well, this here represents 0 to 100% absorption. And so at the very, very tippy bit of that, carbon dioxide is going to represent 100% absorption just in this narrow little band here. Let's look at a different one that doesn't do 100%. Let's look at methane. Methane, at its very, very tippy peak, only absorbs 60%. And so when I go to draw methane, I have to figure out visually on that part of the curve where 60% is, maybe about there. And that's going to be as deep as the well goes for that peak. For carbon dioxide, it's going to go much deeper, like that, because I've absorbed almost all of it. So then what you're going to try and do is each individual group is going to, there are questions that guide this process, but each individual group is going to decide what the strongest absorbing gases are for their part of the spectrum. And then we're going to come back and we're going to mix your groups, and you're going to compare data and come up with the list of greenhouse gases based on the absorption spectra. So we are doing what greenhouse gas scientists were looking at back in the early 1900s maybe. So this was like how we started to figure out, no, earlier than that, much earlier than that we were doing this work. How we started to figure out that each of these gases were able to contribute to what we call the greenhouse effect. And what I didn't do with you guys, because I don't want to lead this conversation, I want you to find this information organically. I did not ask you for the list of greenhouse gases. I did with my elementary teachers because I knew they'd miss one, and I knew they'd miss a big one. But I know you guys won't, so I don't want you to go in there with a preconceived notion. I want you to find it organically. So, ask me questions because I'm sure you're a little confused. But I have rulers, and I have colored pencils, and I have scissors, so any equipment that you want to help. What was your question?
We are to look at the absorption of the incoming radiation by the atmosphere, not reflected off the Earth.
No, you're doing the Earth. So did anything change? Those of you that were not in group 1, you're kind of unique, you've got the sun. But group 2 and 3, when you came together, and group 1, you chime in by all means. Did anything change in your rankings of the greenhouse gases when you came together and saw the whole spectrum instead of just your piece of it?
Yeah.
What changed?
Well, our original data didn't have anything for methane, so when we got other people's data, we got information for methane, so we knew it wasn't ranked at the end with nitrogen and oxygen.
Okay, right. So your spectrum said methane's not a greenhouse gas.
Right.
Their spectrum said yes, it is. Okay, so right there, right there's one easy flip. What about the relationship of ozone and water vapor and carbon dioxide? Did anything move around in your assessment of where they rank 1, 2, and 3? I'm assuming they're your 1, 2, and 3. Hopefully. Yep. Okay.
Yeah.
What's your number 1? Let's start there.
Ozone?
What's your carbon dioxide, ozone, carbon dioxide? Why?
This is an arrow, this is wire out.
Why is carbon dioxide or ozone your biggest absorber?
When we have all 3, are we allowed to have all 3 at this point?
Yeah. Yeah, I'm sorry. When you have all 3, yes. Of infrared. I'm sticking to the Earth now, so.
Okay.
Of infrared.
We put ozone at the top because it was at the highest point in the curve.
Oh, at the maximum. Yep. Yeah. That's a really good point. Is if you're. Is this working? Yes. So if your peak absorption happens at the peak of the curve, that's what you're saying. Is that, well, that's not fair. Let's go back to this one. If it happens at the peak of the curve here.
Right, because the ozone is absorbing almost 100% at the peak of the curve, so it should be a strong.
How wide's the band?
Of the 100%?
Yeah.
Yeah, it looks like from 9.2 to 10.3.
So it's maybe 1 micron
Yeah.
in width. Do you think that has any effect on how strong the gas is as an absorber? The width of the band that it covers? They said that covers 1 micron. Does anything cover more than 1
Well,
micron?
we talked a lot about water when the 2 came together because we talked about like water's down here is like just taking up so much area of the curve. So that's what we talked about most on that.
Yeah, so let's look at something here a second. Water. Okay, so here this is kind of done for you in a sense. Here's water vapor. This is more scaled. Here's water vapor across the spectrum. Here's carbon dioxide. Here's oxygen and ozone, methane and nitrous oxide. So given that this is scaled more appropriately, would your answers change at all?
Yeah.
Do you buy this, that water vapor pops out as the biggest greenhouse gas here?
That's real data. That's real data.
That's real, well, this is kind of a sketch, but yes, it's based on the real data.
We talked about one other thing, and that's like
I'm sorry.
Abundance.
Yes, so you don't know what the abundances are here, right? Are they representative of the atmosphere or not? This is kind of an exercise, so, whoops, sorry. The abundances aren't necessarily representative here. In this plot, oh, where is it? Where'd it go? I'm sorry. I'm doing this to you. I hate when people do this to me. These are more representative. But that's not the whole spectrum. That only takes from 7 to 25. All right, let's go back to your plots. Ignore what I'm doing here. So, ozone jumped out as a big player. What else jumped out as a big player? Water? CO2. And we all understand this is water vapor as a gas, right? Okay, just make sure we're clear on that. What about those in group 1 that we're looking at the sun's absorption spectra? What's the big take-home message from that exercise? What's the big absorber? Ozone, right? Ozone's pretty much the big one there. Everything else was a little tiny blip. I don't have them all up here. This is just the middle one. What about the most abundant gases in the atmosphere? How'd they do? What are the most abundant gases in the atmosphere? Nitrogen and oxygen. So what did they do? Did you expect them to do anything? They don't have a vibrational mode, right? I think we talked about that. I'm on the 3rd time through this day. I can't remember what I said too. Yes, we did talk about that. All right. So they don't have the ability to do that stretching and bending stuff. So we wouldn't expect them to be greenhouse gases, and we just sort of proved it to ourselves with this data that they really are not greenhouse gases. What surprised you, if anything? Or what was, maybe not surprised, but made you really sort of go, I don't know if I would expect that.
You hear about water.
Yeah.
Water vapor.
You don't.
You always hear about carbon.
Right. So I asked the elementary school teachers, what are greenhouse gases? They said carbon dioxide, 1 or 2 said methane, 1 or few said NOx gases. Nobody said water vapor. Nobody said water vapor, which is exactly what you expect, because if you're not really working with the science of this, it's not a greenhouse gas that we talk about. Because, does anybody know why? Why don't we, we don't rank this as a greenhouse gas when you look at all of the work done by the IPCC, the Intergovernmental Panel on Climate Change. What controls water vapor? What controls it? Temperature, right? It's a direct feedback with temperature. So we change the temperature, we change the water vapor. It's very variable, and it has an incredibly short lifetime in the atmosphere, on the order of days. So it can change overnight. Carbon dioxide, we know, when it's in the atmosphere, it has a lifespan of hundreds to thousands of years. Methane has a lifespan of about 10 years. Different gases have a different cycling time that it takes them to get scrubbed out of the atmosphere. And what else? Other than the water vapor, which is interesting, because if you work with this at all or you teach this at all, it's something that you'll be aware of, but it's so not in our literacy, in our conversation about climate change. But every climatologist that models climate change, water vapor is a big part of that, but it's a big uncertain part of the modeling. Because it's also tied to cloud cover, and it's this huge complicated feedback. Anything else pop out as very interesting? What were the other questions on this? I'm sorry?
Does liquid water have a different absorption
Probably.
spectrum?
Probably. I would guess that it would, but I don't know.
Cloud is a suspended drop.
It is, and there's exactly. So what they tend to do is increase the albedo, which is the reflectivity. And so the cloud cover.
The more water vapor goes up in the atmosphere.
Yeah.
So then it cools back.
It does, and there is that feedback. We're going to talk about some of these feedbacks next time, but absolutely. And water vapor, unlike other gases that we're talking about at our atmospheric temperature and pressure, can liquefy and can drop out of the atmosphere. These other gases don't do that. Not on Earth. Maybe on Pluto, they're frozen and they're doing cool things with methane, frozen methane on Pluto, but not here, not on Earth. So what happens, does anybody have any questions before we finish this? Any nagging little issues?
We expected methane to absorb, to show some absorption. There's none here.
Methane. Oh, okay. So let's talk about methane. Perfect.
Now, is that because of the scaling, the accuracy, or what?
Okay. What happens with methane on that plot is that it looks like it kind of gets masked by either nitrous oxide.
Oh yeah, never mind. Yeah, well,
It looks like it overlaps. Where's methane? Wait, right there. No.
this is methane.
There's methane.
Well-
So it overlaps a little with nitrous oxide here.
Never mind, that was
That doesn't
actually a
exist here.
stupid question.
No, it
because
wasn't?
I wasn't even, no, I was looking only at my spectrum.
Oh, you don't
here.
have methane.
And I didn't have nothing, but then of
Right.
course we have to look at the other parts.
You do, but even still, your question's a good one, because if you look at methane, a lot of people say, well, it overlaps with the nitrous oxide, so it's masked by, another gas, or it's overlapping. However, when we look at it really, really carefully, let me show you something here. Methane, I'm just jumping all over the place here. So methane, way down here, this is kind of a slightly different way of looking at this plot. It's flipped this way, so wavelength is smaller here and larger here. They're using wave number, which is I think chemists prefer that. So methane actually fills a gap in the band that other gases really don't absorb. This is why methane's become a big part of our conversation about climate change. And this is kind of what I want to talk about right now. So do we have another question? But methane's kind of part of where we're going, so I don't want to
Are you going to give us
jump.
rankings?
Am I going to give you?
How they're actually ranked?
Okay, so what's the biggest greenhouse gas? This is kind of the rankings here, okay? So water vapor, because it covers such a large part of the spectrum, carbon dioxide, ozone, methane, nitrous oxide, they're pretty much ranked in order there.
Why have we really never heard of nitrous oxide being greenhouse gas? At least I haven't.
What do you teach?
Earth science, well, physical science.
Okay. I'm not sure, because it's one of the NOx, they usually call it NOx because it can be in various different forms, but the NOx gases have been for a long time a big part of the conversation. They actually have, okay, so carbon dioxide has something called where are these numbers? No, but anyway. Nitrous oxide actually has a greater warming potential than methane. Methane has a greater warming potential than carbon dioxide. And then we have all these fluorinated gases that are insane, that have insane amounts of warming potential. I'm not sure why nitrous oxide wouldn't pop into.
I think it's carbon footprint.
We're really so focused on carbon, and then something fun comes out like methane, and we can talk about cows farting, and then that hits the media. So we are so masked by things that sound fun, and nitrous oxide just doesn't have any. There's nothing sexy about nitrous oxide. It comes from burning fossil fuels, and there's nothing sexy about carbon dioxide either. But
Nothing fun about nitrous oxide.
there's nothing fun about nitrous. Oh, ha ha ha! I got it. I took it wrong. Yes, it is laughing gas, so there is that. I had a conversation with my dentist, my current dentist. I said, because I used to see his partner when I was a kid, and he said, whenever I come in to get a filling, Dr. Wolf would always give me laughing gas. And he's like, that's because Dr. Wolf didn't like kids, and that was his way to shut you guys up and not have to deal with you while he was treating you. I'm like, that's great. I loved going to the dentist, though, you get drugged. What could be better? So there are some benefits, I suppose, to an increased nitrous oxide level in the atmosphere, but I think the warming potential might be the downside of that one. All right. So we can probably pop back to our seats so you can find your individual iPads. And if you're able to, let's go. Did we look at this yet? We didn't look at this. We didn't actually digest this yet. So if we were to take all of your absorption spectra and apply it to the black body radiation curves for the Earth, this is what they would look like. Let me try and orient you to what this figure is showing us. So at the top of the atmosphere, this is the temperature. If we were a satellite, I think this one's 12 kilometers out. If we were a satellite 12 kilometers above the surface of the Earth, the upper atmosphere's temperature would radiate here. The Earth's surface would radiate here. This wavy line are those absorption bands. So let's look at this, and let's look at your data and see if we can identify where these peaks are coming from. So right down here close to 4, what's this absorption peak?
That's a carbon dioxide.
That's a carbon dioxide. All right, what about up here, like right before 6? Those of you that had this part of the spectrum.
H2O?
So we had that. What about here, right around maybe 6.5?
Still H2O.
Okay. Then we come up here. What's this one?
That's like 9. Or 8.
Okay. And what's this one? Or yeah, I'm sorry. We didn't. What was that? Like 8.5? No, 9.5 maybe.
Ozone?
So there's a peak from ozone, an absorption peak. I'm calling it a peak. It's really obviously an upside down peak because you're absorbing. What's this one? That's about.
Sphere difference.
Okay, who's above? Wait, I forgot one. What's this one? Right around almost to 8. Well, 7.5-ish.
That's the CH4 nitrous.
Yeah, this is probably a combination of methane and nitrous oxide right here. That big dip. Now, what does it mean? Let's just step back from this and kind of appreciate what this plot means. What does it mean that this curve is high here and low here? Let's interpret this.
So there's more photons at 10 microns than there are 14 microns.
Okay, so if I'm a satellite and I'm looking down, I'm reading a temperature here that's maybe 290, right? And here I'm reading a temperature that's 220. So what does that mean? Which part of the atmosphere am I reading the temperature from here?
That's the top of the atmosphere.
Right. So does that mean we're doing a lot of absorbing there?
No. You gotta be near the ground, right?
Just means maybe that it has to heat it more.
Okay, if I'm reading the top of the atmosphere, that means I'm not reading the temperature on the surface, right? This is a hard diagram to kind of, for me, I really have to think this one through. We're looking at the top of the upper atmosphere. That means we're not seeing the infrared radiation coming through because it's absorbed. We get what we call atmospheric windows. These are areas where a lot of absorption is not occurring. And this is where we have potential, like for methane or fluorinated gases, to really add to the absorbance of infrared radiation, wherever there's a gap in the spectrum. And that's what happens with methane. That's why I want to talk about methane for a bit here. If you guys have Puffin loaded, this is a site that requires flash. It's a pretty slick little visual simulation. Really, I think it's nicely done. Let me see. So I can pop this up and it does what you just spent like, half an hour more doing. And in this case, it's scaled by the global warming potential and the concentrations in the atmosphere. And what pops out pretty readily to us here is that methane fills some of these bandwidths here. Methane is the gray one. Now, I'm going to throw another curve at you and show you the actual emission spectrum for Earth. So even though wait, let me do this. No. Okay, so I think that's all up there now. So this is the absorption spectra, but this is Earth's emitted radiation. And so it's really only this curve that we care about, under this curve, that we care about where these peaks are coming in. So we've got big peaks here for water, big peak here for carbon dioxide. We've got overlapping peaks for, oh goodness, these are some chlorofluorocarbons, these little guys here. And the blue is, I don't even know, octafluoropropane. But you see how water vapor sits up here again and fills up a big part of that bandwidth as well. So anyway, I think this is kind of an interesting little visual. You can play with it in lots of different ways. I won't spend a bunch of time doing it, but let's take that off. But you can look at just water vapor, for instance. I can color it in, and then I can see the vibrational mode of the molecule as well. So just wanted to point that out. All right, so the few take-home messages I want to make sure we got from this little exercise is a greenhouse gas is a greenhouse gas because it will absorb infrared radiation. We've got that. We learned, maybe some of us learned, that water vapor is actually a very large contributor to the greenhouse effect. Climate modelers include water vapor in their models, but because it is a feedback rather than a forcing, so a feedback means that it is influenced by temperature itself, in this case. So the temperature rises, water vapor rises. Temperature falls, water vapor falls. So we do not target water vapor with legislation. It just doesn't make sense. The other thing we may or may not have learned is, oh, do we even talk about this? That the guys that had the sun part of the spectrum, you noted that the ozone was the biggest absorber, right? Most of us probably already knew this in some way or another, that ozone up in the stratosphere is protecting us from that intense UV radiation coming from the sun. And there's a school of thought that who teaches biology? Well, only one biology teacher? Excellent. So there's a school of thought that the creation of ozone in the atmosphere was directly related to the ability for critters to move out from being just ocean critters to being able to live on the land. Because when they lived in the ocean, they had this protective water that helped absorb UV radiation. It wasn't until ozone built up in the atmosphere that they could move safely out of the water onto the land, evolve into land creatures. And so the timing, if you look at the timing of these mud puppies, what are they called? Tiktaalik, I think is one of them. If you look at the timing of when these species evolved, it correlates fairly nicely with creation of ozone in the atmosphere. And so it's kind of a neat little tie-in to biology. The most abundant gases in our atmosphere are not greenhouse gases. Methane, kind of already talked about this, and what I'm going to show you here is a little description of why methane. All right, you know what, let's look at something here for a second. Let me ask you a thought question. If I were to add more and more and more of any of these gases, carbon dioxide, let's use that as an example, would my well get deeper or would my bandwidth increase?
Well, we're getting
Get deeper? Okay, so this is the defined temperature of our upper atmosphere. Is it going to get colder than our known temperature of the upper atmosphere? Okay, so you're telling me if this gets deeper, that means we're going to measure a cooler temperature at the top of the atmosphere. Because what?
It needs to be absorbed from right down below. Are you talking?
Well, this is the temperature we're measuring at the top of the atmosphere, right? It's kind of a known quantity. So can we get cooler? Can we make this peak get deeper? What would probably happen? If we can't make the peak get deeper because that temperature, that 200, we just are not any colder than 220 degrees K at the top of the atmosphere. So what's going to happen? Yeah, so let's look at this for a second. Let me show you a little example. This is a model. This thing. You'd think they'd have a better system set up. Oops, I shouldn't say that on the... I forget that I am being recorded at times.
So are you saying the little peaks that are currently like halfway down, would still come down?
They can, absolutely. But once you've hit,
The Montran model is designed to show the intensity of infrared light that leaves the planet. Because greenhouse gases are selective about the kinds of infrared light they absorb and emit. The Montran model shows basically how these infrared selective greenhouse gases affect the energy balance and therefore the temperature of the planet. The smooth curves here are black body curves at different temperatures. The warmer an object is, the more intensely it shines infrared light. The jagged blue curve is the intensity of light that a virtual sensor at an altitude of 70 kilometers looking down would see in the region of the band of the infrared where the bending vibration of CO2 absorbs and emits light. What you see when you look down from space is the cold upper atmosphere, so the intensity is following along this cold black body curve. And then in this region here, the atmospheric window, the atmosphere is transparent to infrared if there's no clouds. And so when you look down, what you see is the intensity corresponding to a room temperature, like the temperature of the ground. The total rate of energy that's lost to space in watts per square meter is proportional to the area under this blue jagged curve, and it's given here as, in this case, 287 watts per square meter. So we can change the amount of greenhouse gases in the atmosphere and see the impact. Getting rid of CO2 makes this region here more like the atmospheric window region. There are different localities of the atmosphere that you can try out. And you can put clouds in. And see the impact of that. If you want to compare two runs, you can save one to background and then do a second run. And we'll plot the second one on top of the first, so you can go back and forth and see them together. And if you want to show the raw model output, the actual text output from the model, that is here in all of its glorious splendor.
all right, okay, I was thinking he was showing us that, hold on a second. It's this next, this is what I want to show you. So we'll come back to this when we meet again, but just to finish up for today, this is a few different outputs from that Montran model. So right here, 0 parts per million carbon dioxide. Here's what happens when we add 10. What happens when we went from 10 to 100? Did it get much deeper or did it mostly get wider? Yeah, I mean the peak kind of peaks out right here at the bottom of this bottommost curve. It got wider here. What happens when we multiply it by 10 again? It gets wider. So what happens as we add more and more gas to the atmosphere, it will widen this peak. And that's part of what's happening when we dramatically increase the amount of carbon dioxide.
Carbon dioxide only absorbs specifically, is that correct?
Yeah, we didn't look at the whole absorption spectrum. We didn't look at the entire spectrum, but it didn't. It absorbed a little UV, and then a bunch of IR.
So you can just increase the number of wavelengths that it absorbs, or does it already absorb at those wavelengths, and we're just increasing, you know what I'm saying?
We're increasing, okay, so if you looked at a peak from one of your curves, do you have carbon dioxide on here. So what you'd be doing basically is taking this peak here and you'd be widening it when you add more and more carbon dioxide. Okay? Don't ask me to explain why. Don't ask me to explain. You're not cool with it.
No, what you're saying is that, I'm sorry, when scientists compare the spectrum over years,
Why am I getting feedback?
carbon dioxide spectrum has gotten so better that they can say that we have more carbon, more
hold on, I'm getting noise here that I wanted to get rid of.